Hey YouTube, it's Dimitri, and today we're going to do, I believe, time series 17. I'm losing track here. But we already looked at a simple method. We built the simple method, and then we ran some mean squared errors, MAE, MSE, MAPE, so the MAPE. We ran all these calculations, we looked at them. We don't really know too much now. We need to build some other models, look at some more data. But something I don't see a lot of people doing here is listening to the model and listening to your data, right? Do you hear it? What is your data telling you, right? What's wrong with it? Why is it sick? What's the issue we see here? And people think I'm crazy. It's okay. But in general, we need to see what the errors have to say. The errors are more important than the model itself, because the errors are going to tell us the symptoms, right? They're the symptoms of the model, what's wrong, right? It's like listening to the heartbeat on a patient. Does it sound good? Do they breathe good? Is their blood pressure okay, right? So we're gonna look at that real quick. I was gonna wrap it in the last video, but the video is getting fairly long. So let's just dive into how I look at errors a little bit. Again, you could spend, I don't know, a week, 2 weeks probably looking at errors on different models, getting new models, running new calculations. We're gonna dive in here and just talk a little bit about these different types. So we're going to type in here, welcome to time series simple, we'll call it analytics, model, error review here. Would put diagnostics, we'll put review. Okay, so the most simple, straightforward way to do this is let's just plot out the histogram of the errors that we have, or the residuals, we're going to call them. So plot errors as histogram. And to do this, we're just going to type in hist. And we're going to look at dev2. And we're going to type in error. And then next, we're going to put in freq, which is the frequency. And we're going to put false. If you put frequency, it's going to give you the number of errors in that band. So if the model has, I don't know, between 0 and 0.1 error, it's going to say how many you have. I don't want that. I want this as a percentage of 100%. So it all sums up to 100. And then next we're going to type in main equals. This is adding a title. Why it's called main, I guess it's the main title. But we're just going to call this dev2 errors histogram. And if you run this, you'll see we have a nice pretty histogram. Okay, it all fits on the chart. Everything looks fine. Is it normal? I don't know. Hard to tell. You shouldn't just eyeball something and say, oh yeah, it's normal, because it might be, it might not. So let's add a line over this with the normal distribution here. So to do that, we're going to put normal curve. So let me note here, this is the normal curve based on our data, not the standard normal. So standard normal is mean of 0, standard deviation of 1. A normal curve can be any normal distribution, but the mean and the standard deviation, which define the curve, are set by the data itself. Okay, so to do the normal curve here, we're going to need to create something like the data itself. So we're going to set up the x's and call xfit, and we're going to generate a sequence, and we're going to say, okay, the minimum of the sequence is going to be dev2, and it's going to be the errors. And we're going to put a comma, and then put the maximum value, which we want to be the maximum of dev2 of the error. And then finally, the length of the sequence that I want to generate is going to be equal to the length of dev2 error. Okay, we're going to run that. And then we're going to create yfit. So we're going to create the y values for this normal distribution. And we're going to use dnorm, which is a function to get the normal distribution. And then we're going to use xfit in here as going to be the range of it. And then we're going to do the mean. So the mean is what you need to create a normal distribution. We're going to use the mean of dev2 errors. And then also, as I mentioned, so in that parentheses, and then we're going to put a comma, and then put standard deviation is equal to the standard deviation of dev2 error. And we're going to run that. All right, and then finally here, we're going to type in lines, which is a function, so we don't need to set it equal to anything. We want to use xfit, we want to use yfit, and we want to use the color, which is going to be equal to blue. You could set weights and other things if you wanted, but we'll run that. And you'll see here it added this blue line to our chart. So it's kind of hard to see, so let's go back to our code and type in LWD, which is going to be the line width, and we'll just set that equal to 2. We'll rerun that, and you see it gets a little bit thicker here. So is it normal? Probably not. But let's do something else here, which is going to be called a kernel density estimation. I'm not going to go into too many details on fitting kernel density estimations. I use them quite a bit though. So if you want, you can look them up. There's some textbooks that are pretty good at doing them as well. There are academic papers on them. You can Google them, find anything you want. But basically what it's going to do is we're going to try to fit a kernel density estimation, which is going to take different small pieces of data on the density, and it's going to put little tiny curves to create one big curve. But basically it's a non-parametric method of fitting a curve to the data itself. If it fits and it's close to normal curve, so if you plot these out and it's close to the normal one, you're like, awesome, it's probably normal or close to normal. If it has some interesting waves in it, it might not be close to normal, but again, it depends on the parameters you pick for kernel density. We're just going to use the built-in functions without hyperparameter tuning and all that stuff for kernel density. But let's just start off with here. It's pretty easy to do. So you just type in, again, we want to do lines, and we're going to type in density. And then we're going to tell it, we want to do the density estimation for dev2 for the error. And I'm just going to put a comment here and put line weight or width equals 2. And we're going to put color equals red. So it should plot something similar on this chart. And we plot it, and look at this. The red line goes off the chart. It's hard to see. To fix this, we can do this pretty quick. Let's just go back up in our code here to histogram. And in here we can type in ylem, which is the y limit. And then we're going to put in C, so a list. We want the minimum value, the maximum value. We'll start with 0 as the minimum because it can't go less than 0. And it looks like our chart now stops at 0.06. So let's do 0.08. Don't forget the comma to separate ylem from main. And then copy and paste the code that we had and rerun it. Okay, and now this looks a little different. I also want to note here, the data looks different. It looks squashed. The distribution looks wider, right? As soon as we ran that, the distributions look different. This is why it's so important to plot the normal line in like a kernel density estimation, is that depending on the scale of your bars for your histogram, sometimes it can look really normal, and then when you add the lines or you readjust the y-axis, but then add the lines, it looks really different. So in general, I'm going to say, no, this is probably not normal. So let's just put a note here. Errors don't look normal. I mean, they're okay, and we're getting kind of a bell curve here, so maybe we have a shortage of data, which is one reason. This isn't a stats model, so it's not required. Again, this is required for maximum likelihood estimation, MLE. For OLS, you have the requirement of an expected value of your residuals or your errors here. Net has to be equal to 0. So again, there's all kinds of statistical tests and assumptions and all this. We're just building an analytical model right now, so we're not going to consider all of these because it's not really a model, which is why I don't consider it a model, because we're not using stats testing and assumptions. But again, we want something fairly normal. We don't want to bias. Like, we don't want to be over predicting, under predicting. It looks like we're slightly over predicting on part of it for the most part. But again, we have a little bit of a tail on the left. If you look somewhere between, I don't know, -15, -20, that kernel density is a little higher. What's that indicating above the normal means we'll probably have a few outliers that are fairly negative for the prediction. So again, you could sit and look at these charts. You should do this. Come up with reasonings and logic and things and where the model's weak, where you're mispredicting things. And then finally here, we want to actually plot the errors. So you can do this with time series. You can't really do this. You can do scatter plots, I guess, with other data. But for time series, we're going to plot the errors by time, which is super helpful. And to do this is pretty simple. We're going to call it dev2 little t for time. We're going to plot this out. Dev2t is going to be equal to some plot. So we're going to do ggplot, which we've used in the past, the parentheses, and then we're going to do the geom. And again, there's a lot of cool geoms in here. Maybe I'll link the book below again for plotting. I really like the book. It's on visualizing data's weakness. It's on the theory more so, but it kind of trains you how to type out code to use ggplot. And then we're going to type in our AES, and we're going to type in x is going to be equal to date. So dev2 date. And then y is going to be equal to, okay, so don't close that parentheses. Y is going to be equal to our errors here, so dev2 error. And then we're going to put a comma, and we're going to put in the color. It's going to be equal to blue. That's just, or black. So the colors that you choose are up to you. Just for me, for historical data, I typically plot it black. It has to do with my regulatory background and what I've done at other banks. But we're just going to do that, and we can plot that out. And again, col, C-O-L is short for color. Let's just type it all the way out to be safe and better coding practices. You can run that. And I forgot geom line. So if we'll add this line in here, got too excited telling you guys all about the different types of geoms. We're going to run that real quick. And again, nothing seems like it happens because I think we assigned it to dev2. So just type in plot and then put dev2 little t, and we'll run that. And you'll see we have this crazy noisy chart. So a few takeaways from this. What are we looking at here? A, it's going to be around 0. That's what we want. That's good. That's expected. But there looks to be runs in the data. So what do I mean by this is that if you look, there looks like a path or a trend that's going. It looks like when it's bouncing up and down, it's trending upward for a little bit, like in here, and then it trends downward, and then it trends upward, and then it trends downward, and then it trends upward. If you count these, there's 1, 2, 3, 4, 5, and a part of 1. This might be something else going on with the data that's a cyclical component that we didn't fully capture. The other thing to notice here, if you look at this short period, the volatility or how much it's bouncing around is quite contained in one range, and then all of a sudden it explodes and you have crazy volatility in another section, and then it goes back down again quietly, and then it explodes again. This is what we like to call in stats and econometrics as the data is heteroskedastic. So the volatility or standard deviation or variance, whatever you want to look at, is not constant. So this is going to be an issue with stationarity in the residuals. Just by definition, you could test it again. I'm not going to cover every test under the book. It's not a stats model. We'll do it for statistical models. But then we also noted, right, it's heteroskedastic, and it seems to have runs, which means that it's probably serially correlated. And you can test the heteroskedasticity. I'd put money on it that it is. But since we haven't covered a lot of those tests in the time series videos, we did cover serial correlation though. So if you remember right, these are ACF and PACF charts. So autocorrelation, partial autocorrelation. If you don't know what I'm talking about, please go back and watch some of the other videos. But let's just run an ACF test real quick. And ACF2 is the function. And we'll type in dev2 error. We'll run that real quick. You can see here that we have a clear issue. All right, so the ACF function is showing like 9 lags of issues because these bars are above the blue line. We could diagnose these. We could dig into these. I might do it in the next video. We'll think about it. But again, like an ARIMA model, which is a statistical model, you need some type of lag. But what this is telling me, and again, if you go down to the PACF here, it's showing that we have an issue with 1 and 2 and maybe 3 here. And there's also lags. Look out further around 30 days, so we'll think about this. What is significant about 30 days? It's a monthly trend. What's significant about 1 day? Well, that's just simple serial correlation of 1 day. So why is this meaningful? Let's think about this in weather. It's the same for like stock prices, for example. Whatever the temperature was yesterday, we're probably going to be fairly close to that. So if it was 75 yesterday, sometimes it's better to create a simple model that just guesses yesterday's value, right? So you could say, okay, if yesterday was 75, tomorrow is going to be 75. So there's going to be a correlation. You're probably not going to see a day that's 75 and then like 32 degrees, so freezing, right? You're not going to see those big swings. So it makes sense to break that. We might, if we wanted to fix this or look at this in a different light, we might be able to take somewhat of a regression or a model, for example, OLS. You might be able to put in different components and looking at the modeling structure of the simple model, so an annual component, and then looking at a daily lag, so yesterday's value helping us out, maybe setting the starting point. And then finally here, like I pointed out, you see here at 30 lags, we have an issue. There is a monthly component or trend or something tying in there. Does that make a lot of sense? I don't really think it does, but it's important to kind of remember that because we might think of something, or a weatherman who might be the user of this model would say, oh, of course, I don't know. There's some correlation between months. I don't know of any, but they might know of something. It's a small kind of autocorrelation. And then if you actually correct for the daily, this will change the ACF and PACF charts, and you should see different results. So this might fix this. But let's just wrap this video up here, and let's just do our out of time error analysis quickly. Again, this is not all the analysis you need to do. You could go in and do all kinds of fun analysis. You could dig deeper and try tinkering with it. I will note here too, let's put a note in. An alternative to this model, this is an annual, we'll call it an annual average model. I don't know, that's what we'll call it. You could also do an annual, we'll call it a moving average model. So you could say take the last average of the last 2 years, but then that moves forward in time. You could also do an autoregressive model, which would be an AR lagged model of some sorts, where you could say, okay, I'm going to take yesterday's value and I'm going to multiply it by some coefficient. Again, it might be challenging because when you have cyclicality in seasons, we'll have ups and then we'll have downs. So again, you see here that the simple model is not really working, and there's things we could fine tune to probably get those errors smaller. But again, I'm just kind of pointing out there are alternatives, and you could modify this framework and do some fudging to get it to be better, which we might do. We'll think about it. But finally here, let's just do the out of time testing. And to do this, I'm just going to copy and paste what we have up here. So copy the plot, the normal, and the kernel density estimation. And let's see if we have the same trends, patterns, things like that. I don't usually encourage you to copy and paste. Yes, it is very helpful. If you're going to be doing a lot of these, sometimes you can just create like a macro or a function to do this, and then you can just run your function. So it's already pre-built in. You go find a function to do it. But sometimes it's bad practice to copy and paste because you can mistype something. So make sure you understand your code pretty well when you're doing this. So we're just going to change all of our devs to OOT. So we're even going to change the title of the chart. I'm going to leave them the same, so like XFit, YFit, because I'm going to rerun them, and then you run them and then create the plot. Also in practice for coding, you might name them something different like XFit OOT, YFit OOT. But since we're just using these for simple plots, I'm not going to spend too much time in making it fancy and following best practices for coding. And the reason being, I think time is more of the essence than reproducibility for this example and training. Okay, and let's double check our code. Out of time, do you see any devs? No. We might need to adjust this Y limit, but let's just go ahead and run it. Okay, so it looks the same. So let's just check real quick. I know this is actually the right chart, but if you look at this hump up here on the top part of the red line here, so our kernel density estimation, it's kind of dipping but fairly flat. If we go back to here, you'll see there's more of a dip down here and it falls below the blue line. So yes, it is updated. It has new data. Again, though, it suffers from the same issues here. We have too many data points above in the center part of the distribution. Okay, and I believe this distribution for both of these is what we call leptokurtic. Leptokurtic is where you have too many distributions in the middle, which you see here above where the red line is. It's above the blue. And then in the tails, you'll have fatter tails. So out towards the tail part, the red line should again be higher than the blue one. And then in between the tail and the middle there, we should always see the blue line compensating by being higher. And there, the opposite of leptokurtic is platykurtic. I believe it's how you pronounce it or say it. But in general, what you'll end up having is like more of like a shield volcano, if you know what that is. It's like a flatter distribution in general. Your data will be below a normal distribution and the tails will be thinner. I'm not going to go into too many details on this, but anyways, the distributions suffer again from the same issues here. So no, the residuals here or the errors are not normal. And again, this could be caused by number of observations. Meaning if you had more data, it might essentially converge to a normal distribution itself. And then finally here, let's plot out these plots by time. And to do this, we're going to change the color. I don't want black, I want green. You'll see why in a second. Change the dev to out of time. Make sure we change the name that we're creating. This is a common mistake. Sometimes I forget the assignment piece. We're going to plot that. And it looks very similar. So we don't have these really high peaks on the left-hand side to start. It's just where we cut the data, I think. But again, we see this heteroskedasticity where the volatility is quite small in some areas, and then it gets quite large again, and then it gets quite small again. There's definitely a seasonal component, something happening here, something that's wrong. Something cool to do quickly here. We'll just call this full chart or full errors. Full error. Let's just copy and paste the green component. And then we're going to put plus. We'll enter on another line here. And we'll paste again. But this time we'll change these back to dev. So dev2, dev2, and this is going to be black. And you don't need the ggplot or the extra plus here. This will cause an error. And then we'll put enter and then type in plots full error. So what we're going to do here is we're going to compare. So I'll put a little note. We want to view all the errors across time. Okay, so let's run this plot. This is actually a pretty cool one. Okay, so you can actually plot these out. The black part is obviously the development. The green part is the out of time. They make half and half. But again, you see the pattern is consistent with development and out of time. This is fairly good to know because the data is going to be stable across time. So what this means is that even though the model is not the best in many, with many properties or some of the issues of over and under prediction, that, the change in volatility or standard deviation within the data here, it's cyclical and it's consistent across both our development and our out of time. So this is good news in a way because it sucks on one side that we have to rebuild this model somehow and fix these errors, or we could use it and just note that we have all these issues. But it's nice to know that if we fix it in the development set, we should see improvements also in the out of time set. And then quickly here, we can just run this, for fun. ACF2, so we're going to run the ACF, which is going to be the serial correlation testing. We can just do it for out of time. So do ACF2, and then do out of time 2, and then error. Yep. So as you can see here on the ACF chart, it's very similar to our development set. We have issues around lags 1 and 2, specifically with the PACF. We don't see issues with 30 though, so that's kind of interesting. It's kind of shifted out to 40. So again, I don't think 30 makes a lot of sense. I could be wrong, but I don't think it does. I don't see it in out of time. I see it shifts to 40. It's just a random occurrence based on where it is chopped. That's going to be my take on it. That's my hypothesis and story. Again, you could do more testing, like for example, trying to fix these lags at 1, which are big, and seeing if these go away. We also see this weird kind of ACF issue around, 10 to 15. Again, these are kind of going to be weird, normal, some issue with the data. We don't really know what to do with it at this point, but we should focus on the big problems first, which is going to be these lags of 1, and we might consider to fix these in other future videos. Anyways, I hope you guys enjoyed this video. It's a little bit long, but it shows you more what you need to do on the residuals, dive deeper. Again, you could do statistical testing for heteroskedasticity and get a statistical answer on the data. It's not a stats model, but it does help to understand this. This will build into our future models what we're doing. So anyways, thanks for watching. Don't forget to like, share, and subscribe. And as always, until next time.